en la mañana, 19 minutos 42 segundos, tiempo del centro de México. Sigue temblando un poquitito, pero pues vamos a tomarlo con una gran tranquilidad. Vamos a esperar un segundo para poder hablar.
And hi everyone! Our case study focused on ground subsidence occurring in the historic center or Central Historical of Mexico City. So, what is ground subsidence? Ground subsidence refers to the gradual sinking of the ground surface due to the loss of underground support. It is recognized as one of the major geotechnical hazards affecting urban areas worldwide, especially in densely populated cities experiencing rapid urban development and increasing resource demand. Because ground sinking may seriously harm infrastructure including buildings, roads, bridges, and drainage systems, and underground utilities, this problem has gotten more serious. Subsidence has also raised the risk of flooding, interfere with transportation, and risk public safety and economic stability in several cities worldwide. Mexico City is one of the cities most negatively impacted by land subsidence, which is why we choose it for our case study. The historic center of Mexico City was originally built on the former Lake Texcoco, making the area highly vulnerable to ground settlement. Significant earth deformation in the city has been caused over time by ongoing urban growth and rising water demands. Mexico City's tilted buildings, uneven pavement, broken roadways, and frequent urban floods are all obvious signs of the effect of subsidence. Uneven settlement has also had an impact on historical buildings like Mexico City's Metropolitan Cathedral, which is emphasizing the seriousness of the problem. Due to the numerous interrelated elements involved, such as geotechnical conditions, urbanization, environmental effects, public safety concerns, and client conflicts due to water usage and sustainable development, this case is regarded as a difficult engineering challenge. Therefore, engineers must not only address the technical aspect of the problem, but also consider societal, environmental, and regulatory responsibilities in developing sustainable solutions. The engineering problem analysis and the primary causes of ground sinking in Mexico City will next be covered in more detail in this presentation.
From an engineering perspective, ground subsidence in Mexico City is driven by a combination of geological conditions, human activity, and geotechnical processes which together lead to the long-term ground instability. Firstly, the geological conditions of the site plays a fundamental role. Mexico City is founded on a highly compressible lacustrine clay and volcanic deposits from the former Lake Texcoco. This type of clay behaves like a sponge with low bearing capacity and high compressibility, meaning it cannot effectively support heavy structural loads without deforming. From a societal perspective, this reflects a location conflicts where the site was established based on historical and cultural factors rather than geotechnical sustainability. As a result, modern infrastructure is imposed on a weak ground conditions, increasing vulnerability and inequality risk, especially for communities that lack resources to adapt or relocate. Secondly, groundwater extraction acts as the main human-induced trigger. Large volumes of groundwater are removed from deep aquifer to meet urban demand, which reduces pore water pressure within the soil. This issue is further complicated by regulatory challenges and lack of control. In some cases, illegal groundwater extractions further complicates regulations and monitoring. From an engineering perspective, this contributes to uncontrolled groundwater withdrawal, making it difficult for engineers to manage pore water pressure and prevent soil consolidations effectively. This represents a governance failure rather than purely an engineering limitations, because even a structurally sound building will continue to settle if surrounding groundwater extractions remain uncontrolled. Moving on, as a direct consequence of groundwater extraction, the soil undergoes consolidation settlements. When pore water pressure decreases, the clay, particularly gradually rearranged and packed closer together, resulting in a permanent reduction in soil volume. This process is slow but continuous and irreversible, leading to long-term ground deformations. From a health and safety perspective, this directly affects infrastructure integrity. The key issue is differential settlement, where uneven ground movement causes building to tilt, foundation to crack, and damage to roads and underground utilities. These risks are further amplified during earthquake, where weakened foundations may fail suddenly, posing serious risks to public safety, particularly in critical facilities such as hospital and school. In conclusion, subsidence in Mexico City is not only a geotechnical issue, but also a societal and regulatory challenges requiring integrated engineering and governance solutions.
Now we will look at how a civil engineer should deal with these new and complicated engineering problems in terms of professional ethics, following the rules and managing stakeholders. First, our ethical duties. When pore water pressure decreases, the significant settlement puts infrastructure safety and public well-being at risk. An engineer's main responsibility is to take care of human life. We cannot depend on standard designs on the soft leg bed. As demonstrated by the historic Metropolitan Cathedral, we must actively access complex geotechnical data and create deep foundation retrofits to avoid sudden structure failures. Next, we turn to regulatory compliance. This subsidence is mainly due to the management of unregulated groundwater extraction. To avoid further disasters, an engineer must always support and comply with national laws. In Mexico City, engineers must comply with extraction limits set by CONAGUA, the National Water Commission, and ensure that any new water infrastructure meets certain national standards, such as norm -014 for artificial aquifer recharge. Finally, we must manage the conflicting needs of three specific stakeholders. First, the regulatory authorities, such as CONAGUA. Their need is to enforce the law and stop the city from sinking by stopping groundwater extraction. Second, the general urban residents. Their need is uninterrupted access to some groundwater just to survive. Third, the vulnerable residents in the Centro Histórico. Their need is safe housing, but they lack the funds to relocate or adapt. Here is the main conflict. If the authorities stop pumping to save the building, the general urban residents lost their drinking water. If the pumping continues, the homes of the vulnerable residents in the Centro Histórico will collapse.
Next, we will discuss the proposed sustainable engineering solutions for the three main causes of ground subsidence in Mexico City, which is geological condition, groundwater extraction, and consolidation settlement. These solutions are evaluated based on society, environmental, safety, and regulatory considerations to ensure long-term sustainability in real-world engineering practices. Firstly, for the geological conditions of the former lake bed clay, Mexico City is built on highly compressible lacustrine clay with high water content and low shear strength. Its weak soil conditions make the ground highly vulnerable to settlement. The best solution is sustainable groundwater management. The government should reduce excessive groundwater extraction and develop alternative water resources such as rainwater harvesting, recycled wastewater, and surface water supply system. This solution directly addresses the root cause of subsidence by stabilizing pore water pressure in clay layer. It is also supports SDG 12, which is promote responsible consumption and sustainable use of natural resources. In terms of society impact, this solution help reduce future infrastructure damage and flood risk, improving public safety and urban resilience. Next solution is to manage aquifer recharge, or we call it as MAR. This method returns treated water and stormwater back into the underground aquifer through recharge wells and infiltration basins. MAR helps to restore groundwater levels and slow down further consolidations of the soft clay layer. Environmentally, these solutions can improve groundwater sustainability and reduce water scarcity. However, strict regulations and water quality monitoring are necessary to prevent contamination of the aquifer system. Third, land use planning and subsidence rezoning should be implemented. Engineers and local authorities should restrict heavy development in high-risk subsidence zones, especially in areas with very thick lake-bed clay deposits such as Calco and Texcoco. These solutions reduce future exposure to structural damage and protects communities from safety hazards. Although it may limit urban expansion and economic activities in some areas, it provides long-term benefits by reducing maintenance costs and disaster risks. Finally, the consolidation settlement. The best engineering solution is the use of deep foundation system combined with ground improvement technique. Deep pile foundations can transfer structural loads to the stronger soil or rock layer beneath the weak clay, while techniques such as grouting, soil stabilization, and preloading can improve soil strength and reduce differential settlement. This solution is important for protecting critical infrastructure such as roads, bridges, pipelines, and buildings. Although the construction cost is high, it is significant improve structural safety and reduce long-term repair costs. Overall, this solution demonstrates how civil engineers must integrate engineering knowledge, sustainability, public safety, environmental protection, and regulatory compliance when solving complex geotechnical problems. This combination of groundwater management, aquifer recharge, urban planning, and geotechnical engineering is to provide a more sustainable and resilient approach to reduce future ground subsidence in Mexico City.
Next, we will evaluate the societal and environmental impacts of the proposed sustainable engineering solutions for ground subsidence in Mexico City. These solutions are important to ensure long-term urban sustainability, public safety, and environmental protection. Firstly, sustainable groundwater management is one of the most important solutions because excessive groundwater extraction is the main cause of subsidence in Mexico City. By reducing groundwater pumping and introducing alternative water sources such as rainwater harvesting and recycled wastewater, the city can slow down further land subsidence. From a societal perspective, this solution helps reduce infrastructure damage, flooding risk, and threats to public safety. Environmentally, it protects groundwater resources and helps stabilize the soft clay layers beneath the city. However, strict groundwater regulations and alternative water systems require high investment and strong government enforcement. Despite these challenges, the long-term benefits are significant because this solution improves water security and urban resilience. This solution also supports SDG 6 and SDG 11. The second solution is Managed Aquifer Recharge or MAR. This method returns treated water and stormwater back into the underground aquifer through recharge wells and infiltration basins. Societally, MAR improves long-term water availability and reduces future infrastructure settlement caused by declining groundwater levels. Environmentally, it supports groundwater sustainability and reduces dependence on excessive groundwater extraction. However, continuous water quality monitoring is necessary to prevent contamination of the aquifer system, and the implementation cost can be high. Nevertheless, MAR remains a sustainable long-term solution because it improves resilience against future water scarcity. Another important solution is land use planning and subsidence rezoning. Restricting heavy development in high-risk subsidence areas such as Calco and Texcoco can reduce future structural damage and improve public safety. Environmentally, this approach promotes more sustainable urban development and reduces stress on weak soil zones. However, stricter land use control may limit urban expansion and economic activities in certain areas. Even so, the long-term benefits outweigh the disadvantages because it reduces disaster risk and future maintenance costs. Finally, deep foundation systems and ground improvement techniques are important engineering solutions for reducing consolidation settlement. Deep pile foundations transfer structural loads to stronger soil layers, while techniques such as grouting and soil stabilizations improve soil strength and reduce differential settlement. This solution improves structural safety and protects critical infrastructures such as buildings, roads, and pipelines. However, the construction costs and environmental impact are high due to material usage and energy consumption. Despite this, the solution remains essential because it significantly improves long-term infrastructure resilience and reduces the risk of structural failure. In conclusion, ground subsidence in Mexico City is a serious geotechnical and urban sustainability issue caused by weak lake bed clay conditions, excessive groundwater extraction, and long-term consolidation settlement. The problem not only damages infrastructure and increases flooding risk, but also threatens public safety, environmental sustainability, and long-term water security. Therefore, sustainable solutions such as groundwater management, managed aquifer recharge, land use planning, and geotechnical engineering techniques are essential to reduce future subsidence, and improve urban resilience. This case study highlights the important role of civil engineers in balancing sustainability, safety, environmental protection, and societal needs when addressing complex real-world engineering problems.